So it's a pleasure to be here. So I'm going to talk about some of the more recent stuff that we've been doing in my lab over at UT Austin, specifically with geolocation. And I'll talk about a specific task area of doing things like geolocating documents, so providing a specific location for a document. And then that's an example application that I think leads into some more interesting kinds of possibilities for thinking about natural language learning and representations of words. So I actually put some brackets on this because it's about text geolocation and dating, not about text geolocation and dating. So the goal going toward moving away from simply word-based representations of, say, vector space models of word meaning into models of word meaning that are connected to the real world. So I'll go ahead and sort of launch off with this larger question, and then I'll go into some more specific things of a particular application and then come back to this. But if you think about what something like barbecue means, right? If you ask a semanticist, they'll say it's barbecue prime, right? And of course, people who work in vector space models of word meaning will say, the meaning of life is not life prime, it's something else. So we can start thinking about other things, right? And what they'll say is it's some kind of bag of words distribution, and this is what you get if you do a bag of words on the Wikipedia page for barbecue. And I'll note that Texas actually is visible in there reasonably highly. We take barbecue very seriously for good reason. That's one kind of direction that people take it. You can also think about the meaning of barbecue as being some kind of notion of collections of images or features of images that are taken of barbecue, right? You could also think about it as some temporal distribution of barbecue, such as the number of barbecue events per year over some period of time. And obviously barbecue goes right back to the beginning of the evolution of man, all the way back. So it's got a long history, much farther than 1987. It can also be some kind of distribution over the Earth's surface, right? So there's going to be some places that have a lot more to do with barbecue than others. And I actually found with some of the models that we're looking at, you can visualize barbecue over the Earth's surface. I'll show some examples of this kind of thing. And I discovered a really large bump in the Philippines. And I was like, well, what's that? It turns out that the Cebuano people really take barbecue seriously. It's not just food for them. It's part of their culture. And so it's kind of cool when you can see things just jump out at you like that. Of course, what barbecue really means is sort of what this kid is experiencing as he bites into that piece of barbecue right there. That's something that is really hard to get at, right? It's essentially the thing that people who work with robots that run around in the world and try to use language have to deal with, is how does the robot represent this word in their mind, and how do they associate that with real things? So obviously that's a really hard problem, and I've got friends who work on that, and it kind of scares me, the amount of effort they get just to get the robots up and running, right? So I want to play with text, and I'm going to focus on geography and time as sort of the beginnings of ways into models of working with language that tie us to values in the real world. So what got me going on this was Maria Estebar, who works in our Texas Advanced Computing Center and who graduated from our iSchool, had a collection of books from basically the late 1800s that were all about travel around the world. And she was interested in what could we do to improve the accessibility of a digitized collection of books, of these books. So we have like 100 of these. They were done before Google Books came out, and they're nicely curated. They've done optical character recognition and fixed them up. And the idea was, how can we make those accessible to people? And I think, well, these are about travel. Let's visualize, the locations that are mentioned, and be able to actually take a virtual tour through via a geo browser of books like this, right? So that was sort of what got me going on the whole connecting language to geography thing. And then also, I've been talking with Matt Cohen in our English department, who's a scholar of Walt Whitman, and he's very interested in Whitman's use of language of geography and how that connects to how he conceptualized the world. And also, not just looking at, say, the works that Whitman did, but how that connects to other things that were written at the same time. So I'll come back to that toward the end. So these were sort of some digital humanities motivations for getting into this, right? The kind of thing where people working in digital humanities are really interested in talking to computational linguists these days because they have too much text. They don't know how to engage with that text, and they certainly can't read millions of words for themselves easily. So they want computers to do something useful with it for them. So they're very interested in topic models and that kind of thing as well. And I think it's important for us to be accessible to them, to help them use the models and also understand when the models are not doing what they expect them to do. So the thing that we sort of started off with was working on toponym resolution, where you'd go through a text and you'd identify things like Austin and San Francisco, and then you'd try to figure out, well, which Austin was meant, which San Francisco was meant, et cetera, et cetera. And over the years, there have been a variety of essentially heuristic algorithms for dealing with these tasks, where you have things like gazetteers, like geonames, that tells you, oh, this is in Austin in Texas, and it's in this location. This is in Austin in some other state, and it's at this location. And there's something like 25 Londons in the world, and so on, right? So there's the disambiguation task here. That then led us towards some of the other stuff where we're just looking at attaching a single location to a document. And we're kind of coming back full circle toward this task where now given a book, I'd like to be able to plot out what all the different locations are that were mentioned in that book. Okay? And this then goes towards automating things like the Google Lit Trips. This is an effort where people are manually annotating books like The Grapes of Wrath for, as the progress of the book goes, you can see the locations that were actually mentioned in fiction, but with respect to real locations. So it'd be nice to actually be able to do this automatically with some reasonable amount of accuracy so that you can end up with visualizations like this that apparently kids find this a more engaging way to interact with books these days. And if you actually click on a lot of these links, whoever prepared this has some supporting information about what was going on in the book at that time, and maybe even some related links to Wikipedia articles that are related to what was happening.
It was historical satellite photography, right?
Yes, that's right. Yes, we go back in time that way. So anyway, so we're not there yet, but we're hopefully going to be able to start creating these kinds of geobrowsing visualizations there. Now, as part of a project that I'm working on that's looking at machine translation for so-called low-density languages, we have a data set of of texts that are in Kinyarwanda that are also translated into French and English. And the goal of that project is to work on tools for natural language processing and machine translation. But there's also a real interest in the people who work on at the Kigali Memorial Center in being able to map out these testimonies that they have. Sorry, I didn't mention. These are testimonies from survivors of the Rwandan genocide. And they'd like to be able to do things like mapping out where people were at different times in their experience, such that you could perhaps look at larger patterns of movement and what was going on in terms of understanding an event like the Rwandan genocide in better detail. And so you can look at finding things like mentions of place names in a text like this, and then mapping it into a tool like Google Earth, such that you can contextualize it a little bit more. And something that many people are familiar with is Hotel Rwanda. So you can actually see in context where something like Hotel de Milcolin is with respect to where this person was when they were experiencing what they're experiencing. So this is again part of enabling the ability for people who are in digital humanities or in, not even, say researchers in this kind of area, but helping the general public understand a corpus better without them having to go through all the effort of manually coding stuff themselves. This then relates to things like crisis response. The Ushahidi effort tries to help with people who are texting in messages in real time as something like an earthquake is going on, and then trying to get help to them. And there are other efforts, like Rob Monroe at Stanford has worked on to try to aid people in these sorts of situations. You have sort of the task of going and finding, you get a message that might come in Creole that needs translation, and then it needs to also be geolocated so they know where to send help to. But that's all done largely manually. So if we could in some way help out with that process, that would be really nice, so that you could essentially say, yes, that person's there, go send help. So on a lighter note, there's a lot of explicit information that you're seeing in those about place names, but if you take something like "They're on a Boat," right, which is this parody rap song that The Lonely Island did, there's no explicit mentions of place names in this. There is some explicit language, but you go like, well, how could I possibly, yeah, exactly. How could you possibly geolocate something like this? And what it's going to come down to is that the models that we're looking at are going to have some notion of what things like towels, deck, and these other words are actually going to be doing. And so towels is likely to tell you something about places that have something to do with swimming. That might not tell you whether you're talking about the United States or the United Kingdom, but let me tell you, as soon as you start adding those words in there, that's probably a good indication that we're talking about a U.S. location. And you start adding in dolphin and so on, and before long, you might not do too bad of a job of saying that that's somewhere in Florida. Right? So there's a lot of implicit geographic evidence in the words that are used in the song. So, you know, and the song is not specifically about a particular location, but they film it in Biscayne Bay outside Miami. Right? So that's the kind of stuff we want to be able to cue into with our models. Very quick aside. Russ Peterson directs our neuroimaging center at the University of Texas at Austin, and he and I sat down for coffee last year and were talking about what we were working on, and it turned out that we were working on the same task. I was trying to geolocate documents on the Earth's surface. He's trying to essentially geolocate or brain locate the neuroscientific literature with respect to locations in the brain. And so I'm dealing with a 2D surface, and he's dealing with a three-dimensional set of voxels of brain locations. And his interest is, given something I'm interested in, let me give you a collection of papers. Tell me what regions of the brain are activated, or vice versa. Give me a set of brain activations. Give me back literature or even specific response to that. So that's not work that we've actually gone on yet, but the very notion generalizes beyond just the idea of just doing geolocation with respect to the Earth's surface. And I'll give some examples of doing temporal location as well. But all right, so the basic strategy that we use falls into the language modeling approach from information retrieval. And the idea is, you have a whole bunch of texts that have some geolocation, some geotag associated with them, and that's your training data. What you then do is you basically carve up the Earth's surface using some kind of grid-based representation, and then for every little segment of the Earth's surface, I create a little language model, right? And then I have a new document, and I'm going to say, well, how similar is that document to all these different language models, all right? People do this for image geolocation as well, although they usually work in the raw document space. So what we're essentially doing is collapsing a lot of documents, say that all are geotagged to within a particular region, and then creating one language model out of all of those. Okay? So then once we do that, we're able to rank all of these sort of pseudo-documents or these locations on Earth with respect to that text, and then you choose something out of that ranking. You choose a document.
So there's a natural question about smoothing across similar locations.
Yep. Mm-hmm. Something we're doing now. So, and that is useful for some people have found in other work that has used this. In fact, Cheng, Caverly, and Lee have done some of that. So, all right. Although if you have a lot of training data, obviously smoothing matters less. Okay, so, all right, so Geotag Wikipedia, right? There's a lot of geotag pages in Wikipedia. Thankfully, people have gone through and they've provided very nice geolocations for fine places like Baltimore, Maryland, right? So we have geotags. You can just see it up on the top right if you've ever actually looked at a geotagged page in Wikipedia. So we've got actually millions of documents that have geotags associated with them. So hey, we can build a model of language for these locations pretty well. And it includes fine places like Johns Hopkins University.
So is that a thing, geotagging web pages?
A thing? You mean like something that people do?
Yeah.
Yes, it's something that people do.
So I don't think I've ever seen one of those geotags that you were just highlighting. Is that because I haven't noticed, or because
you just haven't noticed?
Or something?
You just haven't noticed.
All right.
That's right. They're all there. And if you go into an application like Google Earth, you can turn on the Wikipedia layer, and you can actually see what the Wikipedia pages are that are, in any location that you're looking at.
Is there a way for somebody to geotag my homepage without my permission?
Yes, absolutely.
Yeah, so there's some layer that people are building on top of it.
It's Wikipedia. You go and you add a latitude and longitude to your web page. So.
My web page isn't in Wikipedia.
Or whatever. If you have a page about you in Wikipedia, if you're such an august person.
No, that's right. That's not
so,
what I mean is there an interface where people can add geotag information to their favorite restaurants and things like that, even if they're not in Wikipedia?
Oh, well, not. I mean, there are many other utility, things like Yelp and whatnot that have geotag.
Google Maps has
Yeah.
Stuff.
Yeah. There's other layers. Is there another question? Okay, so we have these things. Now, of course, these are actual locations. Johns Hopkins University hasn't moved in a long time, at least to my knowledge. It's been around. It's stuck in this this location right here, and you guys are probably pretty thankful about that. However, there are things like ships that have geotags, and they tend to be on the move until they get sunk, or they are created. They're turned into a museum and retired, right? And so this turns out to be one of the things that was interesting in our error analysis later on, where we're like, what are the things that we were making the most errors on? And it turned out to be things like ships. Because, hey, guess what? The text for the USS Hornet talks about its various battles that it was part of in the Pacific Ocean, and then it was actually sunk. I thought I showed right where it was, but it was sunk where in the Solomon Islands, actually. So that tends to that's where it's currently geolocated, but the text is not just about that. So this obviously brings into something that the problem that I'm going to be sort of evaluating on assumes that each document has a single location, but actually a document should be a mixture of locations. And that's one of the things that we're working on next. But for the time being, this is a useful sort of expedient for evaluating these models. Okay, so it turns out that people who tweet also sometimes reveal their location as they're tweeting. So we have a geotag for this user who happens to be talking about places like Redmond and Kirkland, and that's where they are, outside Seattle. I personally don't understand the publicly revealing exactly where you are as you tweet. I think there are some problems with that. I wouldn't want that to be me. I do let people know that my location is Austin, Texas, but it says Austin, Texas while I'm over here at the moment. But at any rate, people have done this, and so that's data that we can use to train on. Obviously, with any of these models, there are going to be questions about privacy and misuse of things where you're starting to do things like predicting people's location and so on. One of my goals is to try to make sure that this is all done on the side of the good and not the evil. But it's definitely something. I didn't expect this getting into doing modeling of books like from the 1800s. That's where I started off on this, and then you end up landing in Twitter, predicting where Twitter users are. So you kind of you can find yourself landing in those places.
So the Twitter example brings something to the fore for me, which is that different Twitter users are going to vary in the language that they use, irrespective of location. And so it seems like you would want your language model to reflect both the location and the individual user. In other words, you could learn a lot about the location by seeing. You might, for example, be able to guess that this Twitter user has changed location, or that something about them has changed because their current tweets differ from their past tweets, even if their current tweets are not particularly symptomatic of Baltimore.
Yep, and what you're talking about there gets toward doing a temporal prediction of a person's location, say, over the course of their tweets, and that's something that we're not, in what I'm going to report, we're not doing. We're aggregating all of the content that a particular user has done, and then we're locating essentially a user. But again, people do have the ability to move around, and we'd like to be able to.
So my question is really about explaining away. So if you have this tweet that looks like it comes from Baltimore, but actually it comes from somebody who uses those words all the time when they're at home in Texas.
Right.
So you might be able to explain away those Baltimore words by another cause. And in the same way for a lot of the things that you're doing, taking the source into account. Did it come from this web page? Did it come from Wikipedia? Might be important.
Yeah, you're going to get.
Different people might use language
Absolutely. I mean, you're going to get very different ways that language is used, and that different kinds of domains use language with respect to location, right? So Wikipedia is they're a geotag because the text is about a location, whereas Twitter users, it's I speak in this way. I'm in this location. I'm not talking about the location necessarily, but I speak in this particular manner. And then that actually cues right into certain kinds of dialectal differences that actually do appear in Twitter, including things like just hashtag innovations, or what was it? We found that the number 2 followed by MM meant tomorrow in a particular part of New York City. And that was the only place that was using that. So you get those kinds of things that go on. All right, so just very kind of quickly, a high-level view about how you might go about locating an article is take something like the Wikipedia page for Prague. What we do is we essentially create this grid, and those grids can be constructed in a lot of different ways. Initially, just assume what we do is we take a square degree grid, so every degree, every cell is going to have the same number of degrees on each side. And then you chop up the Earth in that way. For every document that lands into a particular location like this, we're just going to aggregate all those together to create one long text, a pseudo-document. And then you have to assign a location to that pseudo-document, right? And that location can either be, the centroid, sort of the center of that cell, right? This is just some cell that has a whole bunch of documents located into it. Or you can take the centroid. And we found that just by moving to doing the centroid rather than the center, things work a lot better. So it was like one of those little teeny things that made a big difference. It's kind of boring, but hey, that's something that you find as you do this kind of stuff. All right, so you then generate a language model for each one of these locations based on the pseudo-document. Clearly, you would need to do things like smoothing because certain locations are going to have very few documents associated with them, and so you end up smoothing against a background language model. You can also do things like smoothing against your neighbor, the neighboring pseudo-documents that are around you, so that you use local language to boost your knowledge about this particular location. So those things can all help. Then you've got your query document like the Wikipedia page for Prague, and then you build a model for that. If you're doing certain kinds, if you can look at what's the probability of generating that document given the language models for all of the different pseudo documents that you have. In that case, you're just generating the words that are in that document. If you use a Kullback-Leibler divergence between this document and the each one of the language models for the pseudo documents, you can then either smooth it or not, right? Because then you're just comparing two probability distributions. So anyway, so once you've done that, you go ahead and rank all of the pseudo documents, which remember each one of those has a location attached to it. You rank all of those. You get these similarities, if you want to call it that, where how good of a match each pseudo document is to the input query document, and that'll give you some kind of surface that you can either do something very greedy, like picking the top one, or something where you're doing some kind of clustering over what you're getting out, some like a mean shift over the top K. And one of the things that I really want to do next up is re-ranking on this. So I'll kind of come back to that a little bit later. So starting off, these are the Geotag data sets that we're working with. One is just Wikipedia. We've extracted all of the Geotag documents in Wikipedia. This is from 2010, actually. So you got plenty of documents, right? There's like, over almost 500,000 documents that are geotagged in this particular set. And for what it's worth, there's a lot of work that goes into parsing Wikipedia, even though it has, you can think of it as a semi-structured annotated resource. So Ben Wing, who did the extraction of this, ended up doing an awful lot of regular expressions to capture subcases and so on. But anyway, so that's been done. The other data set is this Geotext Twitter corpus that Jacob Eisenstein and others put together. They were interested in modeling geographic variation in language use, but they also were able to use this data set as a way of testing their models to see how good of a job they could do at geolocating a user. And so then we use that same one. The error measure we use is the distance from the predicted location for a document to its true location that we know from the test set. Some other people who've done work on this will actually do this grid-based thing and then measure the accuracy with respect to the grid. But obviously one of the parameters of any grid is what is the size of my cell, right? And then if you have a larger cell, well, you can get higher accuracy. So we prefer to go with the distance-based measure, because it doesn't matter then what your underlying representation is. And for what it's worth, you actually don't need to use this sort of cell aggregation thing. You could use the raw document space, which is what people tend to do in image retrieval. You just need to have efficient means to find similarity between your query document and the documents that are out there, and using locality-sensitive hashing and things like that. We haven't done that. We're doing the aggregating kind of game. So anyway, so then we're going to report the mean and median over the entire evaluation set, plus the number of documents that you successfully located within 100 miles. And this is just an example of what the distribution in log error distance looks like over the corpus on one of the development sets. So you can see that things generally are bunched up close to, for Wikipedia, they're generally bunched up close toward the true location. But you get this tail of documents that are actually pretty far away, right? And what that does is it really makes the mean error a lot larger. If you have a significant number of documents out there, they're thousands of miles off location. And this happens with these boats, right? With these ships that are out there. You geolocate them to some place in Hawaii, but they're way off in the Solomon Islands and so on. Okay. So the results on this, it turns out to be pretty effective for Wikipedia. Remember, Wikipedia has a lot of mentions of names of people and places and things like that that are really good indicators for location, right? And so we're able to get a median error of about 11 kilometers, right? These are kilometers, not miles. So 11 kilometers on that. And over 90% of the documents are within 100 miles of their true location. So we did 100 miles because that's what another research group had used, because they were measuring stuff in miles, but we are doing things in kilometers. So anyway, that's why it's 161 kilometers. So pretty successful, and that's just the basic approach. It works really well. The Twitter data is quite a bit harder, right? As you can imagine, you're queuing into choices about language use more than aboutness, right? About location. So I'm able to locate you because you use certain word patterns, not because you're talking about Johns Hopkins University and so on. Although that is there, it's just not as prevalent. And you also usually, the documents are shorter.
So when you're trying to do geolocation like this on text or that people are saying, aren't there actually maybe two questions or two things that are conflicting? There's the location where they're at, someone is from New York City, but you can imagine someone who is born in, say, Bronx is going to speak differently than, say, someone who moved to New York City from the Midwest. So there's a language of location, so to speak, and then the language of ethnicity or whatever you want to say, and those are going to be related or not.
Well, and the register that a person uses can vary widely. I mean, my wife is African American, and she will fluidly go between many different dialects depending on who she's talking to, what the context is. And so these things are very, we're not teasing these apart in this particular thing. So hopefully, things are working out well in the aggregate, but one would hope that modeling them better might do a better job.
But so you're trying to actually do the geolocation, like where this person is,
Yes.
not what?
Not where they're speaking about or where they're from. So those are all being conflated here. And you're absolutely right. If one had an annotated data set that was, this person is, in Baltimore but talking about Japan, that would be interesting, right? But you kind of have, you end up with what can you evaluate on problem? So that's where we're at the moment with that. That's really, really good question. So at any rate, so Jacob and group Eisenstein is beating us on the mean accuracy. So in other words, his model is not making as wildly off predictions. Perhaps it's being a little more conservative, but at least on the median, we're doing better. And so we tend to get more documents more correct than his model, but we do really have some howlers, I guess is the way to think about that. And I guess you can see we're about 36% of the documents are within 160 kilometers. So in terms of privacy, at least we're pretty far off right now. we're not knocking on people's doors, and so that actually kind of makes me happy in a way, even though we're trying to reduce this distance, obviously. It gives you a sense that the problem is hard. But nonetheless, if you think about some of the stuff that Mark Dredzy and others are working on with Twitter and looking at health patterns and so on. If you want to be able to look at geotagging all over the entire United States, but you want to be able to use tweets that don't have explicit geotags, if we're talking within 400 kilometers, that's not too bad in terms of looking at how the distribution of use of terminology about being ill is, right? So you could imagine that being at a fine enough resolution. I mean, a lot of people just look at state-level resolution for some of these things, and so. Of course, my perspective right now is coming from Texas, and I grew up in Michigan, which are reasonably large states. I guess if you're talking, Connecticut and Rhode Island, we're not doing so well. But in terms of Texas, great. Okay, so anyway, so that's there. Now, the same basic setup, as I mentioned, can work in other kinds of spaces, such as perhaps the brain, but also with respect to time. And so one of the things that we have looked at in other work is to say, well, can I learn a model of language connected to time and then take a new document and predict when it's about, essentially. And so you can do the same deal. You take the timeline, you chop it up into what are called chronons. These are just the cells on the timeline. Take a document like Abraham Lincoln's biography, and we train this on biographies. So you have an associated range of dates that are associated with text. So you learn your models from that. And then for Abraham Lincoln, you do the same deal. You look at what the divergence is between Lincoln's document and all of these time periods. And we're going all the way back to practically 4000 BC. And zooming into 1700 to 2000 AD, the graph of the similarity between Lincoln's document and each one of those time periods looks like this. And hey, you can predict his lifetime midpoint, as 1835, which is just a little ways off from 1837, which is the true midpoint. So that's one way, essentially an evaluation setup that we have for looking at whether we're able to predict locations based, or temporal periods based on time. And we do this with respect to Wikipedia biographies. And then Wikipedia also has a whole series of event pages. So for every year, there's a list of events that happened in that year. And if you go before 500 BC, there's a lot more uncertainty. So there's events that happen to span several years. But from 500 on, it's everything that happened is supposed to have happened within that particular year, like a particular battle, or so-and-so was made king, blah, blah, blah. And then we also looked at whether we could predict the publication dates of Gutenberg stories based on the language that was used. And crucially, in doing the Gutenberg task, that was trained on Wikipedia biographies to try to predict the publication dates of Gutenberg stories that were completely unrelated. And it worked pretty well. So there was enough consistency in the kinds of things that people talked about. You can imagine like horse and carriage and stuff like that is going to have a very particular time signature to it. And that seems to be enough to do a reasonable job at it.
There's probably also some quotes in the Wikipedia entries from your own writings.
That's true. That's that's true.
Yeah, I mean, that might not skew, but that could occur a few rare words.
Yeah, that's absolutely correct.
So what kind of pre-processing do you do to, I presume you remove dates?
Yeah. So it's only based on the text, the A through Z characters in the text.
So if it was spelled out, you could still get that maybe, or like if somebody wrote out 1854 or something.
Right. So if you combine this with using the explicit dates, your accuracy gets better. Right. So with on the Wikipedia bios, which actually contain those. With the events, there are a few indications of dates, but by and large, there's no explicit mention of dates other than like March and January. And so they're not specific to the year, which is what our prediction task is. With the Gutenberg stories, there's almost no mention. It's fiction, and there's almost no mention of dates. So it works reasonably well. Now, one of the things that you can imagine, though, is since dates can be identified with reasonable accuracy, if you have a good temporal expression finder, and we use Heidel time for this, which is one of the better things for this. All you need to do is now any text that has a pretty high reliability date in it can be training data for you. And so then you can just do a standard word context window to train your models around mentions of dates rather than documents associated with text. That's something I'd like to do next, because then you can get away from, say, the particulars of Wikipedia biographies and the domain that is.
So I want to make a guess that just as ships give you your geolocation errors, your dating errors are science fiction errors. No, but they use particular kinds of things because people have, I think science fiction often gets caught in the current moment. It does, yeah.
And so they actually, that's not necessarily the case. I'd have to look at the
I would think
data.
that, in a corpus of 19th century writings, discussions of space travel would be fairly rare, except in other words, you might just reject that as being 19th century, but actually it was Jules Verne.
Yeah, but again, the choice, we'd have to look at the exact things, but the language choices can be very subtle and really be giveaways. Yeah. Yeah. Yeah, and this comes back to one of the things that I'm interested in with respect to this, which I'll come into a little bit later, but the difference between event time and speech time, right? And if you look at things like dynamic topic models, they build, they're based on publication dates, and then they build a model for language as time goes on. But that's all based on publication dates, not on how people were referring to those dates. And so I'll come back to that later, but I'm interested in, for example, comparing the difference between the 1911 Encyclopedia Britannica and Wikipedia, talking about the same date, the same ranges. And, quite frankly, you look at stuff from the 1800s and so on, and there's some pretty racist stuff in all this stuff, and there's going to be some things that will really jump out quickly, I think, with respect to how people use language to talk about various peoples and so on. Hopefully other things that will be interesting will show up too.
So it seems that there's an opportunity to do something more structured where you look at say the biographies and the events at the same time and try to predict them jointly because
Mm-hmm. Yeah. Yeah. So we wanted to have the events as sort of a held out sort of data set to test against. But you're absolutely correct that there's plenty of.
And the same for the tweets. You may have conversations between users and that might indicate that they're likely
Yep.
facilitated and also.
Absolutely. And there's some really nice work on geolocating people based on basically their patterns of movements and whether or not they happen to show up at the same places enough. So you can actually predict who are friends based on temporal geographic overlap. So there's work on doing exactly that kind of thing, and that would certainly help in these kinds of models, I think.
Is that available in the Jacob Bible?
No, you don't have friendship things in that corpus as far as I know. Yeah. Yeah. Mm-hmm. Mm-hmm. Yeah, yeah. So exactly. And that could come down to simply like which bands are you mentioning, right? In your tweet, you're like, hey, I went to see blah blah blah. I mean, these things are going to be there. So there's a lot of conflation in all this stuff that well, I'll get to it later. I think there's a lot of opportunity for teasing these things apart. So, Okay. So let's just quickly note a couple of problems with the approach that I talked about earlier. One is that these uniform grids ignore the uneven distribution of documents in your training set, right? And if you actually look at this is the Geotext data set. This is the United States. It's a little bit hard to see that, but that big spike there is New York, and then you have LA, and I think Florida is right there. So you can see that this is really dominated by New York. So your baseline prediction is pretty high if you just predict New York City as a geolocation for folks. We went ahead and collected 390 million tweets over like 8 months from last year. So we have a little bit better distribution in terms of over the United States. The graph, the plot on the left is actually showing a small subset of that data that has the same size as geotext. But I basically was trying to generate this yesterday, and my computer wasn't generating the pins very quickly, and I didn't get it in time before I had to go to the airport. But if you actually look at the one that has all of the data, this is pretty much just all yellow all the way through, except for some of the parts in the middle there. But this is the density on the full 390 million tweets that we're working with on our larger data set. Okay, so to deal with this distribution thing, one approach is to build you have a question?
So you've got a new corpus that has the same distribution that New York is way more, but you've got a lot of ones you cover more than that. That's what you just said?
So if you just look at the difference between the two of these things, just by having a lot more samples, we seem to have a better distribution over the United States. So that's all. We weren't specifically targeting that, but it seems that just by having more than 10,000 data points, you get a lot. You get a better representative sample. And it could have been also a time thing, right? So this was collected last year, and the geotext was before, so you don't know about changes in the Twitter population that maybe have affected this. So at any rate, what we want are not even-sized cells across the whole United States. What we'd like are really fine-grained small cells over places like New York and larger ones over places like Montana. So we used KD trees, which are a straightforward data structure that essentially ensures that you have the same number of items in each bucket, and then you you basically partition your space so that you have that property. So then you end up with variable sized cells that can really zoom in particular areas. And this is what it looks like when you do a KD tree over the Wikipedia corpus. So you can see that, obviously in some of the places like Montana, you have pretty large cells, and then things get pretty fine-grained as you head into New York, right? So, that should be useful. So that's one thing. Another problem is that locations don't have uniform speaker populations, right? So this kind of goes back to some of the earlier questions. You've got different communities in the same place that use language very differently. And you can have communities that span multiple locations that use language similarly to one another but aren't in the same location. And so I'll show you that in just a moment. Also just language, period, right? English and Spanish tweets are pretty separable. They're easy to find the difference of if you run any kind of clustering algorithm. And then also just in terms of topics, right? You can imagine that there are places like cities that have large universities, which have university-type pages, and then places that have governmental, that are capital cities. So like Austin has a large university, and it's the capital city of Texas, and that will likely have certain similarities to other places. But we might want to focus on the governmental building geolocated set differently from the university geolocated set, and those will have different distributions over the whole United States or over the whole planet. All right, so what Eric Skiles did in his master's thesis just recently is he said, okay, well, let's cluster all the documents ahead of time, and then we're going to go ahead and create separate such pseudo-document sets for each one of those clusters, right? So it's a really simple way to do this. You can obviously think of more complex ways of actually having a mixture model, say, over a particular location that you do, something more clever. But hey, really simple, first thing first, and it turns out to work really well. Okay, so just note that this is over the same document space, but now we've clustered things, and now we're going to actually end up with different cells, where this would be, one cell for this cluster, but then in the same location in another cluster will actually be two different cells. Okay. So in terms of looking at this on our GeoUT Twitter data set, this is the original distribution of all of the documents. If you then look at a cluster of 4 different clusters, just k-means using the standard kind of stuff that you do, TF, IDF, blah, blah, blah. You get these 4 different clusters. The one that jumps out the most is the one on the right, where you get Spanish language tweets. In particular, we do have some tweets that come from Mexico, but also Texas, Southern California, Chicago's in there, and New York and Florida, right? So that's clearly a distinct community that if you build a specific model for geolocating those, you're likely to do better on. Otherwise, these are comparatively a lot fewer. Right, and in any language model you're building, those words will just get pushed way far down and almost become invisible.
So these are different language models that you use?
So these are different partitions of the original document space, and then you're just going to construct each one of these things. And again, it's just information retrieval. So you can cut up you can keep the sort of raw document space if you want, or you can cut things up. And as soon as you start to cut things up and collapse, you have the potential to lose distinctions like the Spanish language distinction in there. So this is, just separates them out, and then you just build 4 parallel pseudo-document collections, and then you do retrieval against all 4 of those. So that's the basic idea. And New York still dominates in these things, but you can see that the relative proportion of, say, California is higher in this one, and then kind of lowers as you go along. And this last guy over here has quite a bit more through the middle from Texas on up. Okay, and if you build KD trees over those, you can see you end up with fairly different ways of cutting up the United States into different grids. So how does it work? Well, on Wikipedia, just using the KD trees themselves seems to lose a certain amount, and that's probably, if we improve the smoothing, in terms of neighbors, I think that will actually go away. But you can actually use the KD tree with the uniform grid, and that actually works a little bit better than either on its own. But when you do the clustering and you really can hone in on specific language groups, that really improves the mean distance. So in other words, there are fewer documents that we're farther off on. And I think probably a lot of that comes from being able to model things like the Spanish language tweets better and not being as wildly off on your predictions about those. Because what could happen is that there are some places that actually are Spanish language dominant, and then every new Spanish thing gets thrown into that spot, right? Hey, that's a win. That seemed to work better. Okay. So then on the large, this large collection of tweets that we did, when you have a very large number of documents, what it seems is that the KD trees are really good at teasing apart local language choices, right? Because you can zoom into very small regions. And then, so that, the line to look at here is sort of this KD centroid line, where over the uniform grid, we are improving both mean and median by quite a bit in terms of the performance. And then when you do the clustering on top of that, that really reduces the, especially the median accuracy by quite a bit. So so that's happy. The results work out well. So pretty straightforward strategies, but there's a lot left to do. So in all of this, we're still just choosing the top document, which is sort of unsatisfying. So we're looking at doing clustering on the full ranked output. We're not doing the neighboring smoothing, which we should be doing. It's sort of unsatisfying as a guy who does a lot of syntax to just use unigrams, so I'd like to change that. One of the things that I'm most kind of excited about is, there's a clear loss function in this, which is you want to minimize the distance of your predictions. And so the whole learning to rank area of information retrieval allows, basically we use those models that we're using right now to just retrieve a set of documents, and then we can do a re-ranker against that, trying to minimize the distance given some set of training data. But even in that sense, it is still sort of unsatisfying to chop up continuous spaces like space and time. And so, the Earth's surface is kind of tricky. You can't just lay Gaussians over them. You can do it on very local areas, but interested in using things like von Mises's spherical distributions to model locations as mixtures over locations, and then each location has a von Mises distribution around it. So, but things can get a little bit hairy with that. So it's something that we're working on, but haven't been able to sort of move forward yet. One of those things where the student who was working on it had to get a PhD and go somewhere, Tae-Sin Moon. So unfortunately, fortunately for him, he got he's over at Maryland now. But unfortunately for me, it meant he couldn't work on this anymore. So anyway, and that connects to this thing about documents being about multiple locations. There's obviously something sort of ill-posed about just labeling a single location on a document when in fact it's quite likely to be many different locations. And then finally, the thing that sort of leads into this grounding thing that's in the abstract for the talk is that different words sort of have different informativity with respect to these different kinds of tasks, such as time, temporal prediction and geoprediction and so on. And so it'd be nice to be able to learn that, partially just to do a better job on these tasks like geolocation, but also to go towards things like models of word meaning. So the distributions that we're using have these characteristic kinds of looks. So I can produce a probability distribution over the Earth's surface for a given word. So here's a word. Anyone want to guess what it is? It's it's sort of a geological feature. Shore, yeah, so it's beach, right? So here's another one. This is another geological feature. Mountain, yeah. But it can also be non-geological stuff. So this is a word of something that you consume. And over there, those big bars over there are France and Spain. Huh? It's wine. Okay. And then this over here is another thing that you consume. Barbecue, yeah, there you go. So Austin has a big thing right there. So there you go. So this is part of what allows us to geolocate things, right? Is that they have these sort of characteristic distributions over the Earth's surface.
The rest of Texas is small because of the lower population density compared to Austin.
Possibly lower density of using Twitter and so on as well. I'm actually sorry. That came from Wikipedia. I'd actually like to have that graph re-extracted. So I'm going to be doing that. We have a newer update of Wikipedia, so we'll be I think improving that graph.
That's based on how much the Wikipedia page says that this
Yeah.
city is known for its barbecue.
Yeah. So how many pages talk about barbecue that are geotagged? Exactly. So exactly. So then there's obviously regional variations in words on Twitter, and this is something that Jacob wrote a lot about in his stuff. One of the problems, though, is, of course, if you have a smallish data set, it's hard to make generalizations about sociolinguistic variation, and so looking at larger data sets would be quite nice. But it is the kind of thing that allows us to do the geolocation for these users. Now, one of the other things that this kind of goes back a little bit to earlier stuff, but looking at those 20th century travel things, those books from the late 1800s, actually. I should say 19th century travel. I don't know. Why is that there? Anyway, if you do topic models, right, you end up finding that a lot of the topics are pretty much some kind of geographically centric topic, right? And so this is just running a vanilla topic model on these 100 books, chopping them up into like 3 paragraphs per document. And so you end up with these very nicely aligned, topics that are aligned to locations. So we did a simple topic model that just was each location on Earth was a topic, and we tied them to these topics via a gazetteer that would say that if a word was mentioned like Austin, it had to be generated from one of the possible locations that was in the gazetteer. And when you do that, you can find certain kinds of patterns that go over the Earth's surface in terms of word choice connected to location. And I don't want to put a lot into this, but just the moving beyond the specific words connected to locations to things like topics connected to locations, I think is really an interesting way to go. Now, going into time, obviously words have a lot of indication with respect to time. I talked about that a little bit, but it's also in terms of the daily process, right? So if you look at this is not my work. This is I think Alessandro Moschetti and others. If you just look at what people are tweeting about over time and you aggregate their counts of things like breakfast, lunch, and dinner, you can see some pretty characteristic distributions. But again, that you'd expect that for things like breakfast, lunch, and dinner. But you can also look at things like Kanye and Bieber, and those have characteristic distributions where you can see that Bieber's fans are more voluminous than Kanye's fans, but they tend to go to bed by 10 o'clock. Whereas Kanye West's fans are getting up, they're getting up and ready to go. Similarly, you can look at the periodic nature of language choice over the whole year, and you look at things like snow and beach, and those will have characteristic distributions for particular locations. These are actually somewhat tied to location, obviously. I lived in Rio de Janeiro for a while, and we have kind of flipped things around. But you can also do this for things like cookie and diet, right? So you can see that there's this nice trend where people search for cookies and then they try to figure out diets right at the beginning of every year. So you can now go into these sort of sub things. Now, Google Ngrams is pretty well known, and again, this is based on language use over time. And I talked a little bit about this difference between speech time and event time, and how our models are looking at event time and their models are looking at speech time. But you get these characteristic kinds of distributions over time. Let me carry on. I actually already talked about this, but this is just a slide to say what I said earlier about looking at, say, the difference between Wikipedia talking about a particular period of time and the 1911 Encyclopedia Britannica looking at all the text, say, from before 1900 or whatever, and how do they talk about events from those time periods differently. Okay, so then this is just heading towards where Katrin, Eric, and I are interested in going with respect to now using these word representations that are connected to things in the real world rather than just word distributions, right? So if you look at vector space models, they're generally defined in terms of basis vectors that have to do with word co-occurrence counts, and there's your model for beach. And then you can go and compute similarities and do that sort of stuff. We'd like to have that shift to a multi sort of faceted view on word meaning, where we'll have things like geography. So beach is, this is actually real distribution for beach over Europe. And over time, where you might have time actually broken out into a number of different things, such as time over all time that you can measure, time periodically over years, and time periodically over the day, right? And so this is actually what people tweet about beaches. This is search volume for beaches, and then that's beach in Google Ngrams right there. So, you can look at really breaking these things down, and depending on the granularity of prediction that you need, right, you can imagine shifting the weighting of a word like beach, depending on how useful it is as a predictor for these different kinds of time periods.
So one advantage to having these non-linguistic things is that you would imagine that translations of the word would get projected into the same semantic space.
Potentially, yes.
Devin Urowski did some stuff on this actually a number of years ago about the temporal distributions of different words in news text. And so you'd see, beach rising at the same time in English and in Spanish.
That's right. And some of the stuff that Ben and Sean are working on, where looking at things like images and how images are connected to the same, to translations of words. So absolutely, where you're moving away from the circularity of words defined in terms of words to things that you can actually measure about the real world. And so you notice, now one of the things that I'm curious about is taking something like the map for mountain, and you can see, like English Wikipedia, mountain gets to Mexico, and then there's a few little mentions of mountain, in locations in Mexico, but those are all Wikipedia pages about that. But because, if you go back to that old cartoon about the New Yorker's view of the world, where New York City is like this, New York State's like that, and then there's the rest of the United States, we tend to have this sort of, way of looking at our world. But now take Spanish Wikipedia and English Wikipedia and look at what Montaña and how that maps up and see if whether you can find a smooth distribution or change from Montaña into mountain on geographic space without using any text other than that. That might be a way at getting at these kinds of things through non-textual means.
Plus, then you could quantify self-centeredness.
Yeah, and there's some interest. So Simon Overall's interested in this. He's worked a lot on Wikipedia and how different Wikipedias give this notion. So that's sort of there, and then you can imagine adding in images and stuff like that, right? So this then all goes towards sort of full circle. I'm a categorical grammar guy, and one of the things that I'm excited about, and I'm just starting to try to understand in better detail, are things that Ed Greffenstedt is working on, and Stephen Clark, where they're looking at certain forms of categorical grammar, including pre-group grammars, and connecting those to structured vector space models of meaning. And now, one of the points to make is you can sort of insert any basis you like into these, and then the composition happens via the grammar, and so on. And so we could now imagine having models of meaning that will have sort of different loadings for, say, dictionary meanings, geographic, sort of centrality, time, and images, and so on, and then using those as the vectors that you're doing composition on. And so, so obviously something like beach will have a very nice geographic centrality, whereas children maybe not so much. And things like visit are not very easily visualizable. And so, anyway, so our goal is to sort of head more and more toward this, and maybe not just using it in this way, but if you start thinking about the fact that if I have information about how a particular text is located, is connected to geography, we then have all this other data about things like rainfall patterns connected to geographic locations and so on. Can we start to learn things about the grounded world via this indirect connection? Essentially, people choosing to use geography as a particular form of representation that has a very clear interpretation, right? And going toward that. So that's the goal there. So then it'd be really nice to be able to start bringing in more and more context. So taking something like Whitman's writings, connecting it to Wikipedia writings from the same period, bringing in perhaps slave narratives to understand the whole context of the Civil War in Whitman's writings and so on, to adding in these books that I was mentioning earlier and how those relate, to adding in more and more books or things that people are tweeting about. So trying to bring all of this stuff together. And one of the things about these models that I was mentioning is they're all easy to scale up with Hadoop and things like that. They're easily parallelizable. So it's sort of a question of the architecture of bringing these things all together. So I'll just end with saying that Whitman had it right in his Song of the Rolling Earth. It's a really nice thing, so you can go ahead and read that. But he just says, those are not the words. The words are in the ground and sea. They're in the air. They're in you. And it's sort of a nice sum up. And more of the poem actually even has other nice things about it in that sense. So words should be grounded in the real world, and not. We should sort of move away from just text and try to really interact with that. So, and thank you. Questions?
I'm curious on the kinds of errors you see when you're doing the geographic predictions. The one that I think you call them I can't read my reading now. Anyway, the ones that were way off.
The wormholes, or the howlers.
The howlers. Yeah. So, are those? Have you done any kind of error analysis on those? And I mean, I wonder if there's.
Yeah.
I'm trying to think of an example, but if you had maybe you have two geographic locations that are mistakable on a particular search term.
Yes.
If you had a much coarser model, it would say there's no way this is in the Eastern Hemisphere. And so once you made that decision, now you would get the right answer if you did some kind of course-defined framework for those.
Yeah. And so part of the problem are these wormholes. And so, for example, we locate both the North Pole and the South Pole to the North Pole, right? So you get maximal error on the South Pole because of the similarity and what's talked about there. Other things are consulates. So you regularly geolocate a consulate for a country in its own country. And so there's things like that. And part of what's going on there is, huh? Right. I mean, so it's not surprising that they make that kind of error. On the other hand, that gets towards things like going to more fine-grained predictions, like what does downtown mean, right? So if somebody's talking about downtown, that is sort of meaningless outside of scope of a particular location. And I think things like consulate have a similar kind of property to them. And so those are things that we tend to make a lot of errors on. When you have good, when you say Australia, you think Australia, and you go there. The other things are movable kinds of objects like boats that really cause trouble. Questions?
So on that slide where you're talking about treating locations as topics,
Mm-hmm.
I didn't totally follow that, but I noticed on the picture you showed where those were the topics that you had learned.
Mm-hmm.
The little triangle, the
Yeah.
things that you had on those.
Yeah.
So it's really crazy. It has like these circles all over the place.
Yeah. So that's by no means suggested as a good visualization, but the basic this is just get something out there quickly that would allow us to start to visualize this. What it is each one of these is essentially a topic where you have most probable word from kind of going around counterclockwise. So that's all that was. So there's sort of topics that are in here. No claim that this is a great visualization at all, but it was just for us to understand a little bit about how things are distributed. So one of the things that was interesting in that is that you end up with places in East Texas that have a ton of biblical terms associated with them, because there are a number of towns that have biblical names associated with them, and then all of these other biblical terms start coming in.
I thought these swirls were naturally. I didn't know.
No. But
Purposely putting them.
no. So this is just each one of the sort of the cells was a topic, and then we constrained the topic model to if a document mentioned Austin, it had to use one of the Austin topics, one of the locations that mentioned Austin in the gazetteer. Okay. All right, thanks. Thank you.